Hi everyone, welcome back. This is a video near and dear to my heart. Today we're going to be having a look at jump point search in a nutshell. So jump point search is otherwise known as JPS, but this is an extremely exciting algorithm. JPS is essentially one of, if not the state-of-the-art algorithm for pathfinding in 2D and also now 3D grids. So really, if you're a game developer or anyone working in standard grid maps, you should really be aware of the JPS algorithm. It is pretty much on average significantly faster, oftentimes on average 20 times faster than the A-star algorithm that we all know and love, right? Everyone knows A-star. It's the normal algorithm I think people go to kind of solve these kind of problems, and it is great, right, in itself. JPS is going to be building upon the bones of A-star. We're not really separated from A-star and heuristic search. We're simply going to be doing additional reasoning to prune more of the search space, and we'll see that that has significant advantages in terms of speedups. But yeah, so I think very few people seem to be at least understand or implement JPS in their projects, and I think that's such a shame. I think this is one of those things where JPS is a little bit locked behind a bit of the wall of academia. So I hope in this video to slightly demystify what JPS is and to encourage you that you should go and implement this algorithm in your own projects. Yeah, so on average, it's sometimes like quoted as like 20 times faster. It can easily be over 100 times faster as well. So regardless of the few sources on the internet I've seen where like this is ever discussed, and sometimes people even seem hesitant to be like, there's no way, right, that it can outperform A-star in that way. And I'm here to convince you that it can and to kind of show you why. So stick with me. The first thing we should have a look at then is what is the idea behind JPS? How are we going to achieve these speedups? Well, the main idea is that we are going to be doing, essentially, in order to prune the search space to reduce the amount of nodes we need to expand and look at that A-star otherwise would, well, we are going to be doing a strict tie-breaking procedure in order to enforce symmetry breaking. Okay, so what's really important, the baseline idea of why any of this actually works and is performative, is that in standard grid map problems, symmetry is an issue. Okay, so we as humans, the core idea behind JPS is that we have reasoned over the world. We've come up with intuitions and ideas about how we can apply domain-specific knowledge about grids to essentially try to speed up and solve the problem. Well, the idea is we have two different versions of this. I forgot to write this. So there's also an 8 connected problem over here, which is the one, right, where you're allowed diagonals as well, versus a 4 connected problem example I have here. So note that first off, in this video, the standard JPS algorithm works on 8 connected, diagonally connected grid maps, okay? So everything we're going to be walking through is for 8 connected problems. JPS absolutely works in 4 connected problems, and is in fact way faster as well. So you'll even get more speedups in 4 connected problems, but there's going to be a slight reframing from like a diagonal first path, as we'll talk about, to something where you enforce a strict move ordering instead. So then let's jump over here and talk about the issue of symmetry in search. One of the main reasons that search is so difficult is because there are so many different permutations, combinations of equal cost paths, right? So did we go all the way north, then all the way east, all the way east, all the way north, right? And then every possible permutation in between. And you start to see, right, that all of these things are going to be kind of considered in the search space. And this is going to clog up the logic of your standard algorithms. Yes, you kind of get to identify, hey, we've seen this node before. You can prune it or relax it or so forth. But right, we just have this inherent issue in that grids are so symmetric, right, that there are how many versions of the optimal path? This isn't a 3x3 grid. That is tiny. The issue of symmetry is a massive problem. And we'll see that essentially what we're going to be able to do here in a 4 connected world would be to simplify, enforce some move ordering, to simplify all of these combinations to one, what we call canonical ordered path. So what we would do in a 4 connected world is we would enforce a north first move set. So any north move, any vertical move has to happen as early as possible, which means that instead of all of these paths, we have one canonical path. We go all the way north and all the way east. That's the baseline idea. So I'll show as well that this also works for a diagonally connected world in a similar sense. So you have all your diagonal equivalent paths, right? And then think about all of the middle ones in between. There's a million different versions, and then at each of these points, right, you have all of the zigzags and stuff you can do in between. So there's actually more symmetry in four connected problems, which is interesting. Just because diagonally, like, it has to be like the longer axis. I had to draw it longer to show this. But regardless, that's unimportant. How are we going to enforce symmetry breaking, tie breaking between these paths? Well, we're going to do something called diagonal first, okay? So only the version where all diagonals are taken as early as possible is the path we keep. All the other paths, right, they had the same number of diagonals, but they happened at a later time. So it's really like this canonical first, like, prefix, if that makes sense, for your path. That's the baseline idea behind JPS. We're going to walk over here. I'm going to talk through what these diagrams mean, how they correspond to the actual formalized rules, and then we'll kind of bring it back and erase this and do like a big example together of how we can actually draw out the JPS search trace. Okay, so first things first, we're going to look through and explain these. They look scary, but they're very easy to understand pruning rules. What I want to do first is, though, we're making this whole discussion in terms of, hey, we were at some parent P, right? And then we've moved, and we are currently in node X. That's the baseline for what we're reasoning about. And we're thinking, hey, from X, right, if I'm expanding node X, what other nodes might I need to look at? Okay, so we could have reached X, the current node, via either a straight move, right, just straight across, or via a 2D diagonal move. And so the cases are slightly different. When we return over here to talk about the pruning rules, well, we prune things. We get to prune any node that satisfies either one of these two conditions. Number one, the node was better reached, right, reached via a shorter path from P, okay? So you'll see that, like, for example, this top left one here, well, of course, it's easy to reach, right, from one step from P than going from P to X and then diagonally backwards. So that's kind of the main idea, right? We just get to prune. If there's a shorter path from P, well, why wouldn't we have taken that version of the path already? That's nice. The other part then is that we have essentially this idea of the diagonal first canonical ordering I've been talking about. We also get to prune nodes if essentially it was better reached, right? There was a path from P through some other node Y that was diagonal first and had the same cost as the same path through X instead. So what that means is, yeah, we never needed the path from X, we just get to throw it away. So that is where these diagrams come from. I want to draw it here just to show you where this comes in. So we have our two rules, rule 1 and rule 2, and I'm going to show and color in what we get to prune based on each rule. So, right, this node here is, of course, right, we get to prune this because, of course, it's easier to reach via P, right? It's just a one step instead of this weird backward step. So I think that these ones are the easiest to understand. Of course, right? I mean, that one's trivial. Obviously, P from P is, you've already seen it. But now what's also noteworthy is then from P to N, right? So P to N is a root 2, and that is shorter than the cost of 1 to get to X, and then the other cost of 1 from X to N. So root 2 is smaller than 2. So ta-da, we also say, hey, we should have just got here from P. Like, we don't need to reason about this at all right now. Okay? So these are all just the shortest, this is rule 1, right? Just shortest paths. Now, the other versions of this that we got to prune though, is because of rule 2, and this is the diagonal first. So see how from P to X to this node here, that's 1 plus root 2. Well, there's also an equivalent path, right, from P to N to there, or essentially if at the bottom I should use, right? So P to X to N prime is straight, then diagonal, versus diagonal, then straight. So because there's a version from P that does not go through X, that is diagonal first, the diagonal happened at an earlier time, well, ta-da, rule 2 says, oh, we don't need this, we would have found it from P anyway, right? We would have found it in a canonical fashion we liked better. So we get to throw it away. So that's the exciting bit. To show the diagonal one, you can kind of convince yourself, but all of these are just from rule 1. Again, these are closer to P. P is obviously closer to P. And then these two, where it's just 2 straight moves beats the 2 diagonal moves. Okay, so let's have a quick reason over then. How is JPS actually using this? What does this even mean? We'll get to the idea of force neighbours, and then we'll show how it corresponds to this diagram down here. So the most exciting part of JPS, the main like driver behind its speed, is the idea of scanning procedure, okay? Jumping procedure, however you want to call it. So when we're going in a straight direction, we get to throw away all possible other moves. We don't even have to look at them, right? We only ever need to look at one canonical successor, one beam search, right, in one direction. So you get to look all the way up, right? So these hard line ones, like this would be one of our straight scans, for example, right? So you see that for all of them. So there'd be 4 straight scans. We get to just straight look ahead and you get to prune everything else. So there's 2 outcomes of that, right? So either you scan all the way and then you either go off the edge of the map or you hit an obstacle. In those situations, we're going to say that we just get to throw away the whole path, right? All nodes in that entire scan were not useful at all. So that's exciting. Essentially, straight scans are the workhorse of JPS. But we need to take a step back and reason over the idea of force neighbours. When do we need to actually stop? When are there interesting points that we might have needed to look at, right? In order to actually guarantee we still find the optimal solution. Now, as part of this discussion, of course, I didn't really show this, but right, in a similar sense, our diagonal moves do have 3 canonical neighbours. So we have to look at 3 different directions. The branching factor when doing diagonal will be 3. That's kind of what's shown here with the scanning limit. So see how we have the diagonal moves here? And for every diagonal step, you would essentially have to also make sure that you add these, right, node 1 and node 3 as other horizontal scans that you would also need to check, because if you miss them, you may miss an important path that gets us to the goal. So essentially these diagonal moves really just mean what we're going to be doing implementation-wise is taking stutter steps along a diagonal, and every single time you then call straight scans in the other directions. And again, we've just seen that straight scans are extremely fast, right? So that's also part of why this just ends up being such a powerful approach. Now, all of this logic is happy days when we are in complete open space. But of course, we're not always in complete open space. When there are obstacles, right, they can block part of our symmetry breaking, and we need to make sure that one version, right, one canonical version of an optimal cost solution is still within our search space so that we can find the goal correctly and with the correct optimal cost. To do that, it's really cool. We use a really creative way of essentially saying that, okay, we are going to turn at obstacles. What this means, the idea, why is it called jump point search? Well, we will identify in this location here, this node X is going to be called a jump point. What we're looking for is we do our scans, and either we get to throw away everything or we find a point of interest that could be potentially useful. That is going to be a turning point essentially, and we call them jump points because we jump all the way to them, right? So here we do the scanning procedure. When you're doing your straights, you get to happily throw away everything where there aren't obstacles. So in this example, right, if there was nothing underneath, there were no obstacles underneath as I did the scan, we could just throw away all of that, right? All of that information still, which is nice. However, if there was an obstacle at some point in time in the row above, we would identify that and we have to stop and check and generate what is called forced neighbours. I will draw this. So a canonical neighbours I've been drawing in these circles will distinguish forced neighbours with squares. So first and foremost, we still will at some point continue in the straight direction in a canonical sense, right? For the same reason, this is still the necessary path is through X. Straight is still a promising direction. Now what happens though is that essentially these 2 positions here are going to now be forced. It kind of irks me that I wrote 2 and 3 backwards, but I can't erase that easily. So why are these forced? What does it mean to be forced? Well, if you think about it, this force node 2 here, beforehand there was a path from P directly to that node that was shorter cost path, okay? But now there's an obstacle. This diagonal move here is blocked. What that means is that the optimal path, the best way to reach this node, has to go through X now. Okay, and so because this could be important, it could lead to an optimal solution or an optimal shortcut or whatever else, we need to stop at X, generate our jump point, and then add these as successes that we will generate. So for a similar reason, now 3, right, instead of having the diagonal first path, well, the diagonal first path was blocked, so we have to go through X as well. Now, some of this comes from the idea of corner cutting, okay? So if you'd read the original paper from like 2011, 2012, JPS looked a little different and these rules would look different. Just note that as of like 2014 or something like that, for a very, very, very long time, the grid-based path planning competition, like this research yearly open competition to evaluate and compare our algorithms, as well as really just the field as it's matured, well, we no longer allow corner cutting at all. So in the past, this path from P to X, right, this diagonal move here, was just allowed. But if you think about it, right, this is an obstacle, yeah? So in pretty much all realistic scenarios, your agent has some form of size, okay? It's not a point agent. So your robot, your drone, whatever else, yes, we've approximated the grid to represent obstacles. This could absolutely be a real building, a real wall, right? And in that case, if you allow this, you could absolutely just hit it, right? And your path is completely infeasible. So these days, we don't allow you to do that. We reason that your agents are not point agents. You haven't blown up obstacles arbitrarily and then like lost solution quality. No, you're representing the environment as faithfully as possible. And we say, no, you would have to take the detour, right? And that is why that this diagonal here is not allowed. Okay, I'm going to then erase this and we're going to walk through and draw up the JPS search trace. Okay, so let's do an example of JPS. I've drawn up some helper functions down here to get started to explain the behavior of what we're looking for. So essentially the start node is by itself the only node that's different in terms of the directions we need to look. Instead of looking in like canonical or forced neighbor directions, right? Like these are how we expand nodes. From the start node, we have to look everywhere, okay? That kind of makes sense. You don't have any canonical tie breaking to do yet. You'll need to make sure that you explore all directions just so we never miss anything. For 2D scans, remember every time we take one 2D step, we stop and we have to do our full horizontal scans before we continue in case one of those scans finds something, right? And then we really need to stop to make sure we generate things effectively. And then of course, when we're doing the horizontal scans, which are a really fast idea, I'm saying horizontal scans, it's the same as vertical, I mean straight, right? So when we do our straight scans, well, we're happy days until if we find an obstacle, we have to stop, we generate our 2 forced neighbours and still our canonical neighbour in the same direction, and then we would explore those and we could continue onwards. So that is how JPS as a foundation is working. So let's get started. I'm going to draw essentially in yellow the actual search, and then I'll keep pink to represent the actual nodes, the only nodes that we actually stop to generate and put in the open list, right? So we'll see that JPS expands and generates far fewer nodes because of all this additional reasoning and scanning we're doing, which just lets us throw away entire like swaths of the search space. Okay, so from the start node, we will have to explore in all directions. So I'll do one scan down. So we'll go all the way. We either find some interesting things below and stop and generate whatever, or we go all the way to the edge of the map and then we stop. So what I'm representing by all these dots around the edge of the map is I'm saying that, hey, this is like a little subset of the map. Pretend it's much larger, right? And the example still works exactly the same. The one simplification I have made though, just so it's easy, is that these bunch of walls go all the way down to the bottom of the map, okay? So the only way to get to goal, to G, right, the interesting point we want to observe and see the behavior of is to go up and around. Okay, so we would do the other straights. The ordering of this really doesn't matter, so this is up to you. Here is an example, right? This straight hits the wall, similar to the edge of the map. Again, we've found nothing interesting. There was no obstacles near us to stop. So we throw away the whole path, okay? This is the different direction because we start going up and then we stop. So here we identify a jump point, right? Because this location here was forced. There is something we can get around. So we need to make sure to stop essentially and say that this should be forced. This will be canonical, but this is also forced, right? If you follow your idea, it's the 2 blocks after an obstacle that we have to scan in that direction to check. So what we're doing here is we generate this as a successor child, but before we get to come back and expand this or look to see which one we want to expand, well, we need to complete all of our jumps, okay? So you start to take this diagonal, and then you realize that it gets cut off, right? Because again, this is the corner cutting scenario, right? So you would not be able to continue. So that would be the only diagonal step that's taken. When you do this diagonal step, you still have to try doing your horizontal scans, right? So you'd try doing this, you'd see it's a cost of 0, we immediately cull. But you do have to then also check all the way this way as well. So even though JPS is extremely fast, you see how there's some interesting behaviors that's kind of built in here? We're doing a lot of what we would call redundant scanning, right? Or it's not particularly redundant, but we know as human beings that it's in directions that are very unpromising. And that is interesting, right? Especially like this behavior is mostly built in just from this initial start node. Because we'll see once we've expanded the start, well, now we start to expand nodes in order of course heuristic value, so we really beeline towards the goal quickly. But yeah, this is just interesting to note. What's interesting here, sorry, with this straight scan though, is that before it continues, it stops here. There's another jump point because we're doing a straight and we have the same situation. So we stop and we say that these are the directions we will need to continue in. I'll just leave this here because I'll show you, we'll kind of draw that up at the end anyway, of what the full thing would look like, right, without the explicit order of node operations, node expansions we'll look at. So, okay, so we take one diagonal step. We need to do our horizontal scans, our straight scans. I keep saying that, but I'm doing that for no reason. Ta-da! And you would continue this procedure all the way again, unbounded until whatever obstacles at the edge of the map you're hitting. Similarly here, everything just looks the same, so I'll start speeding up. I have a full video on JPS if you really want to really understand these concepts. So here I'm just doing the slightly faster version because this is all about in a nutshell, giving you the intuitions of how it's working. So we take one diagonal step, we do our straights. Sorry, I should draw them to the edge of the map. Maybe I'll get rid of that. Then we come back and we do one more diagonal step. Then we do the same thing. The order of which straight you explore first is again implementation specific, but you're going to need to do both no matter what, so it doesn't particularly matter. Now this is the interesting point, right? Because this scan over here again identifies a jump point. And we now have 3 new directions that we would generate this and have to look at. So here is also now where there's a distinction between what we call JPS 1 and JPS 2, okay? So the original paper says that we would stop at this location, right? Because one of the straights on this diagonal found it, this is actually the point we stop at. This is the jump point. This is the jump point where we give it these directions, okay? Right, repeat directions, by the way, things we've already scanned before. You will then repeat these straights, which sure is very quick, but then you identify this jump point and then you actually generate and add that to the search space. So see how the default JPS is it's kind of described in terms of these single jumps, right? Oh, because this thing identified a successor, we stop there. So what we do in JPS 2, which is now the de facto implementation, it's just more performative in general, and it's the standard way we implement JPS. It's the same thing, but what we're doing is we're identifying between what we call intermediate jump points, IJP, and forced jump points, okay? So if you think about it, there's 2 different situations here. This node here didn't actually have any forced neighbours, right? It was only a jump point because it found another jump point in its recursive call. So what that means is these intermediate points, we don't actually need to stop at all. If we were to have made sure to continue. The reason we stopped at here in the original JPS is we haven't continued along this diagonal, right? And this could be really important. Yeah, so we can't just throw away this node. We can't just stop here and say we're done. We would need to continue the diagonal the whole way. So this is what's a forced node, of course, forced jump point, because it actually had a forced neighbor. So what JPS 2 does is instead of stopping here, right, in order to make sure that we do the diagonal, JPS makes a compromise. It says, we will do all diagonal scans, not until you find a jump point, right? We wouldn't stop here. You do it all the way until the edge of the map, okay? So that has potential downsides in terms of this massive overscanning, right? If that was a useless like direction, we're forced to continue that thing the whole way, okay? But what it does do, what it saves on explicitly, is a number of redundant work, right? We wouldn't have to rescan these things we've already seen. And it does not stop and add and generate and have to do all the heap operations of this node here. It just adds this one directly, okay? So they're both the same thing. Just want to really point out JPS 2 is the de facto implementation. We won't stop here. We'll do an unbounded, right? We will continue to do this diagonal scan with all of its, of course. And essentially what we're doing is we're keeping a list. We track all of the jump points we find on all of these other potentially interesting things, and we will generate all of them. So that is something to keep in mind, but ta-da. So, and that's kind of where some of this other behavior would come in. Okay, I do want to just show what everything would look like. Well, I've been doing this as straight lines. Again, you see how much work, how much scanning JPS does. And remember, every straight scan is really, really quick. We'll look at after this as well the idea of what we call block-based reasoning. Why a really cool, easy implementation trick. We do some bit shifting operations to check these entire scans. So we can stride in like 32 or 64 word like stride lengths, right? So we can scan 64 cells in one bit operation, which is a massive portion of the map. So JPS is just so effectively implemented in usually we use C++ so that we can have the control over these bit shift operations. And that's really where the speed comes into this. But you can absolutely implement this in something like Python and still get good speed ups. Now, before we go over here and finish the example, I do want to show you though, that if we were to continue this, see how we start getting these weird like overlapping of areas we've already searched. So because we essentially had, we force neighbours around the same obstacle, we can start getting silly things. So when you did that, right, what I didn't show is when we do this straight here, this is a forced neighbour, okay? And then this forced neighbour generates this, right, which is very silly. We know as a human it's silly, but JPS has to check this. It's unaware, right, that it's done a silly thing. And it happens the other way too. So there is a lot of potential overlapping of regions. Now consider all of these potential issues and still note how much faster JPS is than A*. It's pretty cool, right? So it's a really interesting algorithm, and I've been reasoning about these kind of overlapping scans, and there's so many cool like additional tricks and implementation hacks that can really like help to reduce or eliminate these issues altogether, right? In terms of overscanning, repeated scanning, so forth. You can essentially kind of also like use adaptive or constant bounds to kind of like limit the jumps in non-promising directions, and there's a whole bunch of research that's super interesting about this as well. For the fundamental idea though, I'll draw it just in terms of JPS 1 because these were the jump points, but if you think about it, of course we expand the start node first, okay? Then essentially, even though these might have been slightly closer, of course, this node here was going to have a better heuristic value, right? So this node would have been expanded. You would have done this. So essentially, the path so far looks like this. Then we find this version, right? Because again, this is really the jump point that's getting closer to the goal. So that's where it's like we still have A*-like behavior, right? We're expanding nodes by their F values. Here, before you find the goal, you do have to do the standard like annoying additional scans, right? Just in case you miss something. So the ordering of that could be different again, but because it's in the jump point, you kind of have to do it. But then ta-da, we finally find this additional scan, and what we have is when we do our horizontal scans as well, our straight scans, well, we also have a check to know the goal distance, right? If we're in the same column or row, well, we can identify that once we step past the distance of the goal, we should definitely stop. And that helps ensure, right, that you never ever miss the goal in this situation. So we would instantly stop here, generate this as a jump point at the goal, and of course that's the most promising. So we will stop there and expand the goal to da, we're done. So JPS, right, if you think about the JPS path here, well, I'm going to call this node N. I'm going to call this node N prime. So in JPS 1, we have essentially the path becomes S, N, N prime, G. So there were only 4 nodes we had to expand in this entire problem, 2 of which were just the start and the goal. So that's really cool too. So think about all the heap operations we're saving on as well. By doing this additional reasoning, which we're seeing, the straight scans can also be implemented extremely efficiently. We don't have to maintain this massive open frontier anywhere near as large as A-star. And we get to avoid all the stutter stepping, right? We did this fast scans here to identify none of this region here was important or over here, whereas A-star would do this kind of radial outwards, right? Everything here looks really good to A-star. It is going to stop, expand, and generate and put in the heap and maintain the heap for all of these nodes in this general region. And we were able to get around all of that. Now, JPS 2, right, as I talked about, it actually just does straight to N prime. So it is even smaller. JPS 2 is the de facto implementation. I would consider looking at that. That's the one that is on the Warthog repository. I'll link to that. That's kind of where we're working on that. Maybe I didn't mention at the beginning as well, like, yes, I'm really involved in JPS. I think it's an amazing algorithm. But yeah, my PhD supervisor, Daniel Harabol, well, he is the original, or one of the original authors of the JPS paper. So it's been amazing working with him. He's a massive inspiration to me. And yeah, so the Warthog repository is coming out of the Shortest Path Lab from Monash University, which he heads. And that has implementations, the original implementations of JPS. It's completely open source, so you can go have a look at that. Now, the last thing I'm going to do, I'm going to quickly erase this. I want to draw up very quickly what block-based reasoning is. How do we implement this super fast scanning procedure? Then essentially we'll be done. But what I want to discuss very briefly first is this procedure is extremely powerful, and this works in a bunch of different domains. So yes, it is kind of doing grid-based reasoning. I think people are working on hexagonal reasoning, which is quite exciting, or like generalized pruning rules for different kinds of environments. But for now, we have so many different variations of JPS that's working now. So I worked on implementing JPS in 3D grids, so in voxel grids. So that is now the leading voxel planner. There is JPS Plus, which is essentially the offline. We do this as a pre-computing step, right? You store all of the jump points and you use that almost like a compressed path database. It's like we can later on, right, when the goals swap and things, if we store all of this information, we can execute extremely quick search by doing using this essentially as pre-computation. So JPS Plus as pre-computation is really performative and supports a lot of state-of-the-art algorithms. As I talked about at the top, JPS 4 connected absolutely exists and it is quite useful. So I'll write some of these down. So JPS 4 connected, JPS 3D, JPS Plus. There is also JPS W, so we've also adapted now JPS to work with weighted grid maps. So one of the original issues with JPS is this procedure is awesome and amazingly fast, but it didn't work when you had different regions of like higher cost, right? Maybe there was some quicksand, some trees or whatever, and so in your game dev world, even though you're storing as the grid, you weren't able to use JPS because the reasoning didn't extend. Well, it now does. We do kind of like a pre-computation step to store information on the boundaries of these weighted regions, but we're able to now make JPS work and be optimal and efficient in these environments as well, which is also exciting. So yeah, let's quickly talk about then how we're actually going to do these straight scans really quickly. Okay, so the last part of our JPS journey is going to be the idea of block-based reasoning. This is how we're going to be essentially implementing our scan, our jump, look ahead, and our straight directions in terms of this large, what we would call essentially a stride length, right? We can get substantially further. We're able to reason over a bunch of nodes at the same time. So in the original JPS paper from 2011-2012, that paper described the pruning essentially on a one node basis. So you would do it one step at a time. Well, with the improved version, I think from the 2014 paper, block-based reasoning comes in and we realize that, wow, through some really nice bit tricks and bit shifting, we can really like cement and lock down this idea that allows us to do this procedure not one at a time, but over an entire word length. So this entire discussion is going to deal with the idea that we're using as an example an 8 8-byte word, right, or 8-bit word, so a byte. That is kind of just like a standard notation, but know of course that in practice what we're doing with modern machines is we're usually taking either 32 or 64-bit strides. So we're looking at 32 or 64 nodes in one operation, which is really exciting. Everything we'll work through here is just an 8 as a simple example to kind of get us understanding the concept. So from the get-go, the reason this works is that we are storing our grid map, right, as ones and zeros, simply as what we'd call a bit field, right? So your entire map is stored as essentially like a 1D array of the map, like map dimensions, map width times map height, where every single node has like an ID equivalent. What that means is just that like we're storing the entire thing extremely compactly as just ones or zeros. Is it blocked or is it free? Okay. So let's correlate this to that idea. So what we're going to be doing is we are, again, similarly moving. It didn't matter where P was, but here, yeah, we've taken a diagonal step from P to X, and we, because of the diagonal step, we have to do a horizontal scan, right, along this axis. So the really cool thing is, of course, because you have to do both vertical scans and horizontal scans, what we do as another trick is we actually store 2 versions of the map, okay? So there's one version of the map where it's, I mean, because you read memory entries, right, in a contiguous byte, all of the ones and zeros of representing this part of the map is right next to each other, and we can extract that from memory at the same time. That's not the case when we have to jump between like rows, right, or what would be the equivalent of row, like massive jumps of the width of the map. So what we do is we store a rotated version of the map, rotated by 90 degrees, so that we can do both vertical scans and horizontal scans equally as fast. And storing the map is usually only a few megabytes, which is really not that bad. Now, what we have here is essentially that we have to do this horizontal scan. So we are working with the word of 8 bits, right? We look at this 8 region here. We're going to call this byte X, okay? So byte X has a bunch of zeros for all these free locations. There is a 1 right down here because there's an obstacle, and then the remaining 2 cells are also free. What we're going to do is we, of course, while we do these scans, we have to reason over force neighbours, right? Are there obstacles above or below during scan? So what we do is we also read in similar bytes for the row above and the row below. Okay, so the row above is completely empty, it's completely free, so it's just all zeros, which is nice. But we will see, right, that as we're scanning, well, we will hopefully identify that at some point in time, we will have to stop here and generate this as a forced neighbour. We would attempt to generate this forced as well, but it's unreachable, right, via the diagonal move. So nonetheless, this is an important forced neighbour to identify because of these obstacles in the bottom row, and that are the 2 ones that correspond here. So how are we going to actually, in the implementation, come up with knowing when to stop? And then over here, I'm going to show you an example calculation of doing one of those force calculations themselves. So there's a couple things. We need to identify, there's 2 reasons to stop, right? The first one is a dead end, meaning that you kept your horizontal scan all the way, and then right, we hit this obstacle here. So in a standard sense, if we hadn't found any forced neighbours, we'd get to stop. We don't need to continue striding, and we throw away the path because we've said, hey, we hit a wall, there's nothing important here. So in order to calculate dead ends, what you do is you essentially check, right, within the current byte, a dead end is detected if there's a non-zero, well, if there's a 0 entry at I, and then immediately afterwards, right, the next location is blocked, which means there's a wall. So today we'd get to stop essentially at location index I. We go, cool, this is the last cell that's free, I'm done. If there's nothing here, throw it away. But of course, as I said, we need to identify forced neighbours as well. So that is where this comes in. So in order to detect forced neighbours, well, you do some fancy bit shifting operators here. What we're looking at here is, this probably is not familiar to you. If it is, congratulations. But this is what we call a bit shift operator, okay? So this is what we're drawing as a right shift. So you're going to take all of the bits, well, I've actually drawn it up as the example here. We are taking this byte here, so the byte below, right, correspond, see how that's the 2 obstacles here. I have the same forced neighbour we want. So the standard byte is represented as 0011 0000. What we do is we're shifting this entire thing 1 location to the right. So this leading 0 here gets pushed off the edge and lost, right? And then because we had nothing on the left, well, a 0 also enters in. So see how everything's just shifted across by 1. These two ones have shifted down to here. So that's all we're doing there. And then we also have the not operator. So the exclamation mark means essentially invert the binary values, right? So all the 0s become 1s, and all the 2 1s become the 2 0s. So what we're doing then is through some bit twiddling, right, really, we construct these two variables, and we're going to do an AND, like so in C++ or whatever, we're just talking about binary operations. And AND says that when we combine the two of them together, the only non-zero elements, right, this non-zero element is when both of the bits, or when both of the binary values are true. So see here that these two 1s, these are the only place where both of these two bytes have, right, the non-zero bit. So ta-da, we have identified that, yes, in this case, one of them was non-zero. There is a force neighbor, and we can extract its location using just basic operations that are already built into your computers or your C compiler or whatever. And you'll get out that the position corresponds to this location here. It really is straight up the location, right? So there's 1, 2, 3, 4, 5. It's the 5th location. Ta-da. Now, also note this whole explanation, there's like, whether it's like left to right, left shift, right shift, it all depends on whatever like little or big endian. It just depends, like, am I thinking about the problem with the smallest bits on the right or the largest bits on the right? It's just very muddled. I think this is the version I show students because it's very intuitive, right? I'm shifting it right so you physically see it shift right on the board. Okay, so now you identify both of these two things, your dead ends and your force neighbors. The stopping criteria generally is that you have to check all of the possible reasons to stop. So you do that by like using an OR operator, right? So you're saying, hey, if anything was forced above, or if anything was forced below, or, right, if I found a dead end in the current byte, in the actual row we're currently scanning. In any of these situations, we have that there will be a non-zero bit within BS, and we get to identify that and stop. In the implementation thereafter, you will reason over the location of that stopping point to identify whether or not it was based on a jump point or based on a dead end. And then, right, so if it was dead end, obviously we throw it away. If it's a jump point, we stop. We generate that as a valid successor, and we then need to generate as well the children that you would need to expand in those directions. So yeah, this is why JPS ends up being so quick. We're able to really succinctly do these massive strides very quickly through some really clever bit twiddling tricks that yeah, just really abuses the fact, right, that our maps can really concretely and compactly be stored in contiguous bytes, in contiguous sets of information that we can retrieve very quickly and use to do our calculations and to do our identifications. So anyway, this has been Jump Point Search in a nutshell. Thanks for watching, and I think JPS is a really exciting algorithm that really deserves more of a spotlight, and I think it's usually because people are a little concerned with how to implement it. So I hope this video has helped there, and I will have a video on how to implement the code behind the scenes as well. So thanks for watching, and see you in another video.